In this video, the procedure for assembling the parts to build a geodesic dome is shown. This assembly is for the method of construction taught in United States Patent Number 8539735. This demonstration is being organized by the inventor of the method. As can be seen, this yellow pentagon is formed from second lower level pentagons and will be the first part used to begin the assembly. It is relevant to note that the assembly using this method starts from the top and proceeds from the top downwards. This hexagon is formed from second lower level hexagons. In the patent, these parts are referred to as frustums. For this prototype dome, these parts are made from radiator pine timber and 3 mm thick sheet metal. As can be seen here, the inventor of the method, Jeffrey Belikovsky, is holding a miniature soccer ball which the method is based upon. The skeleton of this geodesic dome that is being assembled uses a second lower level pentagon starter frustum that has a side length of 300 mm. An understanding of the starter frustum is critical for an architect who intends to use this method to design a geodesic dome, because all calculations, including the calculation for the diameter of the completed dome, are obtained from the side length of the lowest level pentagon starter frustum. For the architect who will use the method disclosed in the patent, this will be easy to understand as a theoretical construct. That being, side length of the lowest level pentagon frustum gets bigger, the entire dome will inflate. Here it is important to note that before the skeleton of the dome can be assembled using this method, it is imperative that the ground be leveled. It is essential that all side faces of all frustums and the entire assemblage are labeled, because once the structure is assembled, it might at some point need to be disassembled and then reassembled once again. After the dome is assembled, labels will be placed around the side faces of the frustums. Each joining side of each frustum will be labeled with the same identical code. As can be seen, the adjoining frustums are being fastened. 2 bolts will fasten each side. It also can be seen that the holes drilled into the frustums are being drilled using a template. It is good practice to drill the holes on each side of every frustum in the same position. It is relevant to note that this dome is being constructed from a second lower level assemblage. From a practical perspective, the second lower level is the simplest skeleton that can be utilized using this method, and only for small domes. This dome, when it is entirely assembled later in the day, will be 4 meters in diameter. For a larger dome designed using this method, for example a dome of 10 meters in diameter, it will be essential to form the skeleton from a lower level assemblage. For a 10-meter diameter dome, the best design would be for the top 6 frustums to be formed from a second lower level assemblage and the bottom frustums formed from a third lower level assemblage. This will ensure that the bottom frustums are robust enough as to not deform under the weight of the top frustums. It is imperative for the architect to understand how to use a combination of lower level assemblages in the design of the dome in order to prevent a deformation of the lower part of the dome. In this section, Jeffrey is going to derive an equation for the length of the starter side piece that will be required when the diameter for a geodesic dome is chosen. In the patent specification, there are 9 examples with solutions. This video demonstration leads on from the patent, so this derivation is entitled Example 10. The diagram that's now being shown provides the basis for this derivation. In this section, Jeffrey will show the geometry that is relevant for the assembly of this geodesic dome. He will show how the interior angles in the hexagon and pentagon are derived. He will also show the angles in the triangle and rhombus. These interior angles are important for an engineer to know who is planning on building a geodesic dome using this method. The coverings across the surface of the dome are a combination 6 mm thick polycarbonate and 6 mm thick high-density polyethylene. Most of these coverings are white, but there are a few that are dark-tinted. The white high-density polyethylene is excellent for the dome because of its thermal properties and its strength. Also, a natural light emanates inside the dome when the sun is shining onto the polyethylene. If one of these domes is built in an environment that could be affected by bushfire, then the coverings would need to be a combination of ceramics and tinted glass. The polycarbonate and polyethylene shapes were supplied by Plastic Australia, located in Arncliffe, Sydney. The ripping and rebating of the timber was done by Bib and Brace Joinery, located on the central coast of New South Wales. The steel angle brackets of 108 degrees and 120 degrees were laser cut out of 2 mm thick steel plate at the Unique Metals Laser Factory, located at Wetherill Park, Sydney. It's significant to note a characteristic of these geodesic domes that gives them true value is that these structures are extremely strong. These domes are so strong that no hurricane or tornado could pull them apart, no matter how ferocious the wind gust. The robust strength is intrinsic to these domes. These domes could be thought of as being a mesh in which every frustum in the structure pulls on every other frustum directly connected to it. These domes would be ideal for coastal communities across the east coast of the United States that are regularly affected by hurricanes.